Your
Okay.
slide and voice both are fine.
Okay. Thank you. So, okay, as Partha said, so I'll basically try to go through some of the basic things in 1 hour. Hopefully, I'll finish in 1 hour, and then Shilpi will take over. Today, so I will basically discuss about the basic concepts of uncertainties, probability, and probability distributions. Uh, where is my slide? Yeah. Okay. Now you can. So I have listed some reference books if you want to, have more details. So you can go through those reference books. Some of the plots also I have taken from here, though many of them I have made. Okay, now let's start. So let me start with the question that why do we need to, I mean, why we are doing the experiments. And we do experiments because we have basically two motivations of doing experiments. Either we try to determine some parameter, say we have some unknown parameter of some model or something that we want to measure. For example, you want to measure the velocity of light or gravitational constant and so on, like this. You are doing some experiment. The other one is, say, hypothesis testing, that we have some model or some theory and we want to check whether that theory is valid against the data. Okay. And in reality there may be some degree of overlap. That means determining parameter can also testify whether the theory is valid or not. Okay. Now when you do measurements, we end up, I mean, we always estimate some uncertainties, or in common words we tell it as errors. Okay. So why do we determine uncertainties? Because it gives a degree of accuracy of our measurement. Say, like, when you do some measurement, if we do not have any uncertainty, then we cannot really say how good is our measurement. Okay. Or to know how far the measured value is compared to your theory or the previous measured values. And also it can help to test a theory. For example, you can say, okay, my measured value is a this many standard deviations from the theoretical predictions, or say previous measurements. Okay. So that also helps to test your theory. So if you do not say have any mm, uncertainties, then for example, as I say, give some example. So suppose you measured some values of the gravitational constant with your measurement, and then you have different, you got some errors. Depending on the values of the errors, you can make some statement. For example, if your error in first case it's say uh, 0.002, which is consistent with, say, you can say this is consistent with my previous number within this, as the error is bigger than the previous measured values. And if it is much, if your estimated uncertainty is much smaller, that means you get very precise measurement. And if it deviates from the previous result or the theoretical prediction, then you can say this is inconsistent with the old one. So uh, there is some possibility of variations and so on. And if the error is too large, then you can say that my accuracy is too low, so it is better that I perform a better experiment than the current one. Okay. So based on your error, so you can quantify your the result of your experiment, or your results. And then you test also your theory. So how many type of uncertainties that we usually encounter? So we have basically two sources of uncertainties. One is random errors, which are basically inherent quantum fluctuations, or there are some random measurement errors without even quantum effects. And then there are systematic errors, which you can say like these errors which are related to the measuring device. Like there are some mistakes in calibrations or offsets, or errors in theoretical predictions. That is, say for example, you calculate your cross sections, you leave out higher order terms, so you have uncertainties in the theoretical predictions and so on. So those are related to the systematic errors. And these factors, when you estimate, in principle these factors can be known, but in practically you cannot always quantify all the sources of these errors, though you can only broadly classify they are random or systematic. Okay. So when you want to quantify these uncertainties, we use the concept of probability. So now let me come to what is the probability. You usually have some ideas about probability. Let me discuss a little bit basic concepts. So the probability can be defined using the set theory. Say we start with some set S with some subsets A and B. So the Kolmogorov axiom so defines the probability. It says that for all A, which are subset of S, the probability of A is always greater than or equal to 0, and the probability of the whole sample space. Sample space is the space which contains all possible elements or all possible random values of your variable. So the probability of S is 1, that is expected, and then the probability of A and B if the probability of A and B is non-null, then the probability of A uh, or B is simply can be written as probability of A plus probability of B. Sorry, I made a mistake. So this should be null, not non-null. Okay. Then from these axioms, you can derive further properties of the probabilities. Okay. So these are the other properties. So you can say like probability of A always lies between 0 and 1 because it cannot be bigger than S, and probability of A bar, which is A S minus A kind of. So it's 1 minus probability of A because A is a complement of A bar is complement of A, and so on. So you can get all these things. Okay. Now let's define conditional probability. So what is conditional probability? So you need to understand this very well so that you can understand also the correlated distributions. So when you define conditional probability, so you say the conditional probability of A and B, if B is not 0, then you can write probability of A given B is probability of A and B over probability of B. So you can see that from this picture. Say here A and B is given like this. Okay. And probability of A is written like say A over the whole set S. Probability of B is B over the whole set S, while the probability of A given B is only this much, right? And similarly the probability of B given A is this. Okay. Now if A and B are independent, in that case you can write probability of A and B is simply a product of their probabilities. In that case, the probability of A given B is simply the probability of A. Okay. Okay. Now from that you can say that the probability of A given B times probability of B is same as probability of B given A times probability of A. That you can see from this picture. So when you write this one, this is basically this portion times this would give you the probability of A and B. Similarly, probability of B given A times probability of A will also give you probability of A and B. Okay. And from here we get a very important theorem which is called Bayes theorem. So now we can write probability of A given B is simply the probability of B given A times probability of A over probability of B. Okay, which is called the Bayes theorem. So how do we interpret this Bayes theorem? Now, as you can see, what we get here is that probability of A given B here depends on probability of B given A times probability of A. That means we have say we have some degree of belief on A initially. Now after knowing what is the um, value of B or whether the B is true or not, okay, our degree of belief changes. Okay, so that means probability of our degree of belief in event A is changing after we know whether B is true or not. Okay, that means before knowing whether anything about B, we have a degree of belief on A, and after knowing something about B, our degree of belief changes accordingly, okay, or updated. So that's our interpretation. Now let's go a bit deeper. Now suppose we can divide the whole sample space into several disjoint subsets, AIs, okay, as this in this picture. Now I can we can write S as the, say, sum of the UIs, okay, and there is no overlap between AI and AHA, okay. Now consider some subset B here, and B is a subset of S, then you can write B as simply B and S, or B and or of all AIs. Then you can write or of B and AIs, right? So then if you do this full algebra, then what you get is that probability of B is simply sum of probability of B given AIs times probability of AIs. So this is called law of total probability. So then you can rewrite the Bayes theorem. So earlier we wrote that uh, in the denominator we had probability of B. Now we can write the probability of B as the sum over probability of B given AIs times probability of AIs. So here this A can be, any other set A or one of the AIs. Okay. Okay. Now uh, once we understand this, sorry, I did not mention in the beginning. If you have any question, please stop me. Otherwise, or you just raise the hand or just shout. Okay. Otherwise, you will maybe missing what we are discussing. Okay. Now let's use this Bayes theorem to solve a problem or understand how it works. Now let's take an example. Suppose we consider that there is a disease T carried by, say, could you go through the slides again? Okay. So if you understood what it is in slide 9, okay, now let's try to do another way, write the same thing another way. Let's divide this whole sample space S into several disjoint subsets. So you can see here that all AIs are disjoint, okay, they don't overlap with each other. Okay. Now if I have some subset B, okay, then we can write B as simply B and S, because B is anyway a subset of S, okay. And then since we can write S as OR of all AIs or sum of all AIs, okay, then if you do this full stuff, then you end up with this equal to probability of B or AIs, okay. And this probability of B or AIs, according to the conditional probability definition here, can be written as product of probability of A given B times probability of B. So I'm writing this factor here as product of this factor. Okay. So then you can write this as probability of B as simply sum of the probabilities of B over given AH times probability of AH. That means basically you can say that these sums are basically the regions, these ones. Okay. Is it understood? I hope so. And then you can rewrite the Bayes theorem where the denominator is probability of B as simply sum of the probabilities of sum of these terms, okay, or the sum of these regions. Okay. Now let's use this theorem and consider this example. Now suppose we have you know what is this? I cannot see the full.
Difference between statistical and systematic errors.
No, they are equally important. It's only that their source is different. Statistical errors, for example, if you think about some experiment, if you have done, say, very simple experiment, which is say gamma ray spectroscopy, which is using some calorimeter detector, okay. So say some sodium iodide or something like this, and so you have different sources of uncertainties coming from here. Say for example, when a gamma ray enters the detector, it produces scintillation photons, which is a quantum mechanical effect. So you have fluctuations in the number of scintillating photons that are produced, and then when the scintillation photons enter the photodiode, so there is a inherent quantum efficiency, and that there, then the quantum efficiency is not constant. I mean, though it is some number, but there is a fluctuation there. So there are several fluctuations that enter. Then you get at the end, when you get some results for each particle, you get different um, outputs. Okay, so that's say random source, for example, random uncertainties. But if you have some calibration offset in the detector or something, so that will correspond to the systematic uncertainties. Okay, so but if your equipment is much more accurate, then the systematic uncertainty only can be smaller. Okay, but the random statistical errors will still be there. Okay, now say for this example, say suppose we have these probabilities, that probability of having the disease is very small, say only 0.1%, and probability of not having this disease is say very large, 0.999. So this disease is very rare. Okay, now consider that so when we have some disease or some symptoms, we perform a test to know whether the we have that disease or not. Suppose there is a test that identifies the disease and the result is positive or negative, so it's like 1 and 0. So suppose the probabilities to correctly identify a person with positive disease are say 98%, and incorrectly identifying a person is 0.02%. That means, in say, if you do a test, you might even if you have say a disease, you may not get the disease. That's 2%. Okay, now similarly, suppose a healthy person but have some symptoms and does the test. Okay, so it correctly identifies that healthy person. That means it gives a positive result without having the disease. That's 1%, and gives a negative result without having the disease. That's 99%. That's sort of expected, right? Now, given this, now suppose you some person goes to the test, performs a test, okay, and then gets a positive. What is the probability that person person has the disease, or that person is supposed to have gets the disease? Okay, so that's the question. Sorry. Yeah, okay. Now how do we calculate this? So we can use the Bayes theorem here to calculate this probability. Now what we want, that initially we know what is the probability of having the disease, which was say only very small, so 0.001%. Okay, now we know this quantity, that if we have disease, what is the probability of getting the positive test result, and if we have no disease, what is the probability of getting positive test result. So if we use this quantity, then if somebody is tested positive, what is the probability of getting having the disease, right? So that we can calculate using this theorem. So we can write this probability of having the disease given the positive result is the probability of having the probability of getting positive result having the disease times probability of disease over the sum of both cases, that is getting the positive result when you have the disease plus getting the positive result when you do not have the disease, right? So then when you do this calculation, what you get is this comes out to be 0.089. Okay, so that's the posterior probability. That means if somebody test the positive, the probability that that person actually have the disease is only 8.9%. So there are two views. So from here you can interpret it differently. So if there is a patient which just randomly test it, test it, okay, and then gets a positive result, then the patient's view will be that the probability of for him to have the disease is only about 9%, while the doctor's view will be that about 9% of the people like this kind of positive result will have the disease. Okay, that's how we interpret this. Okay, now now that we discussed some basic concepts about probability, now let's see how do we interpret these probabilities. So we there are two definitions of probabilities. Um, so one is called the frequentist probability, and the other is Bayesian probability. The frequentist probability is the one that you are all familiar with, which is called basically the relative frequency. So that means if you have some um, trials or something or some experiments and that produces some results, say these are the outcomes of some repeatable experiments, then the number of times you get say x out of the total number of um, trials is gives you the probability of getting the x, right? So that's the um, relative frequency. Say for example, you can say this this can be from repeatable experiment or from observations, repeatable observations and so on. So for example, if you say what is the probability that monsoon reaches India in first week of June, so that's you can take the observations from last many years, and from there you get a probability that how many times um, and the monsoon reaches in first week of June, so that gives you the probability. And similarly, if you say like probability of producing a certain particle in pp collisions at a particular center of mass energy, so you can simply get you can repeat the experiment and you see how many times you get that particle, right? So that gives you a probability. So, and in this case, you can see that this satisfies the Kolmogorov axioms. So, probability of x is always greater than equal to 0, and probability of all possible outcomes is h1. So, that's consistent with the axioms. Now, we have another definition of probability, which is called subjective probability or Bayesian probability. So, this is the basis for the Bayes theorem or Bayesian statistics. So, in this case, the probability is basically is kind of a statement or hypothesis, okay, that something is going to happen, or it basically assigns some degree of belief to a particular statement or particular hypothesis. Okay, in this case, the outcomes x and y's are basically the hypothesis, or you can say statements that are either true or false. Now here you can assign the probability p of x is basically the degree of belief that x is true. Okay, so for example, if you make some statements like this, that what is the probability that it will rain tomorrow, so that you cannot predict using repeatable experiments, because you cannot say what is tomorrow, you cannot repeat that experiment. So this you can have some degree of belief, and based on some data that belief may change. Okay, for example, you have some predictions from meteorological department and so on, so on, so you can change, you can have your belief change of beliefs, so that you basically assigning some beliefs to that statement that it will rain tomorrow. Similarly, what is the probability that the mass of sushi candidate or sushi particle candidate is between say 2 and 3 TeV. Okay, so that's we cannot do unless we find that particular particle. So beforehand, you can only assign some degree of belief to that statement. Okay, and that's why actually this subjective probability are many times associated with unknown constants, which basically reflects one's confidence that some value lies in certain intervals. Okay, like as I said, this statement that sushi candidate is between 2 and 3 TeV, either it will be in that range or it will not be in that range. Okay, so in this case also, uh, you can define the sample space S, which will be basically also called the hypothesis space. This will consist of all possible elementary hypotheses that are mutually exclusive. So among all these elementary hypotheses, at least one of them has to be true. Okay, So if you do that, then it will basically satisfy also the Kolmogorov axioms, that is probability of a given statement will be, or given element will be always greater than or equal to 0, and probability of the whole sample space will be 1, because at least one of the statement has to be true. Okay. Okay. So now, okay, now let's see some interpretations here. So as I said, this is the basis of Bayesian statistics. For example, suppose you have some hypothesis H, and you perform some experiment, and you obtain some data or observations. Now, given the data, your hypothesis, the probability for this hypothesis will change based on this. So you can say initially you had this your belief or probability P of H, okay, which is called the prior probability, that basically indicates the knowledge or degree of belief in that hypothesis before seeing the data. And then you had the data. So given the hypothesis, how the data is compatible with that probability of compatible of this compatibility of that data with this hypothesis, and given that information, you can recalculate what is the posterior probability of um, having this hypothesis to be true given the data. Okay. So here, this, as I said, this one is the prior probability for the hypothesis. Then this is called the likelihood of observing data given the hypothesis. Okay, and this is the posterior probability of whether the probability of having that hypothesis true or false given the after seeing the data. Okay. uh, though we have this equation which comes from this Bayes theorem, but we usually do not have any general rule for assigning what is the prior to the hypothesis, as this is very much subjective. Okay, but what all this tells is that given a prior or given your belief, it can you can recalculate, you can calculate the posterior probability in light of the data. Okay. 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 Now, I discussed basically some basic concepts about probability. Now I will come to the probability distributions. At this point, are there any questions?
I don't see anything in chat, but
Okay.
if anybody, they can raise their hand and ask question. Yeah,
Okay.
no.
I don't see any.
Yeah.
I hope they understood it. So now let's come to the probability distributions. So first, let's see what is a random variable. So random variable is basically a variable that takes some specific value um, or for each element of the sample space. That means, say, if you have say for example, if you have a dice and you throw a dice every time, you get some different number every time. So that's kind of random variable. Okay, which takes different value at every trial. And so the outcome of that random event is not predictable, but we only know the probabilities of a possible outcome. Like, if you throw dice, as I said, one dice, so you have equal probability of getting 1 to 6. So that is kind of uniform probability. And random variables can be discrete or continuous. Okay, as in this case, the example that I gave, it is a discrete between 1 and 6. And suppose we have a random variable, and the outcome of that experiment is a continuous random variable x, then we can write the probability for x to lie, say, between x and x plus dx, which you can write like p of x in x and x plus dx. It's simply f of x times dx, where f of x is called the probability density function. Okay, and since this is a probability density function, and since the total probability of the sample space has to be 1, so you can write integration of this probability density function over the whole range of the sample space is 1. So that gives you the normalization condition. So some question came, sorry. uh, let me go to that. Probability of age given data depends also on probability of HH. Do we also update HH as we get more data? Yes, so as you get data, you can update the HH. So you can actually the your belief or the posterior probability can change, and you can reuse that probability to posterior probability as again the prior, and use the other more data to you know recalculate it. This kind of I think there will be an exercise today, I guess.
Yeah, I was
Uh,
saying that there's an exercise on
yeah, so
this.
you can do
We'll
that.
know.
Okay, so you can update your probability, yes, but you cannot use the same data, so you have to have say new data also. Okay. Okay, now yeah, so this was for the continuous variable. Now we can rewrite also the same thing for the discrete variable. So in this case we can assign a fixed number um, between 0 to 1 to this for each of the discrete variables xi. Okay, so the probability of xi to be f of I, and then the normalization condition ensures that the sum of all the fi's to be 1. So you can write actually the discrete variables or discrete distribution in terms of the continuous PDF formalism, that you can rewrite say f of x to be basically sum of I f of I times the delta function. Okay, and then if you do again the integration of f of x dx, so that you can write sum over fi times the integration of the delta function, that gives you 1 only when x is equal to xi. So that basically makes again the same normalization condition, so that these two are equivalent. Okay, now as I said, the example I gave earlier is a single dice, which is basically say the uniform distribution between 1 and 6. Now consider an example which is you throw two dice together or simultaneously. So then every time you will get 1 to 6 between each of them, and then you will have if you basically the total outcome between the two dice will be always between say 2 to 12, but you do not know the possible outcomes that you will get is between 2 and 12. Okay, but the probabilities, you cannot say which value you will get in before throwing, but you will only can say what is the probability of getting a particular outcome. Okay, so that probability will come like this. So as you can see here, the possible outcomes are 2 to 12, and the corresponding probabilities that you will get will be between 1 over 36 to up to 6 over 36. Okay, so you can see that the probability of getting 2 is small, also probability of getting 12 is very small, while the probability of getting say 6, I think it's 7, right? 7 is maximum, so that's 1 over 6. Okay, so this is actually you can calculate this if you simply add two uniform random numbers. Okay, and calculate that the PDF of the sum of the two uniform random number will be triangular. So you can see that this is actually a triangular distribution. Okay, now, given a PDF, we can calculate statistical indicators like mean, sigma, and the other moments. So, suppose we have a variable x with PDF f of x. So, the mean, the population mean or expectation value is basically defined as the integration of x of f of x dx. So, that's say we say usually the mu, and the variance, which is sigma square of x, is basically the deviations of f of x over the whole range. So or deviation of x over the whole range, so that's defined as x minus mean of x square times f of x dx. So that's basically x square expectation minus mu square, and sigma we usually call it the standard deviation. And for a PDF, this is basically the width of the PDF. And in case of the discrete variables, so you can rewrite this stuff as simple the arithmetic mean. So uh, for mean, you can write this 1 over n or times sum of the xi. However, for the variance, you will have 1 over n minus 1 over and sum of xi minus the mean square. Okay. Okay. Similarly, you can calculate actually the all the moments, the kth moment of x, which is defined as mk or x is x square k f of x dx. So that's the moment, and then also the all the central moments, which will be like x minus mean x to the power k of the expectation of that this quantity. Okay, and the mode of a PDF of
Arun,
f.
there is a question.
Sorry.
Um,
Why there is n minus 1, not n in the denominator of variance? Yeah, that's a very good question. But I'll come back to this when we discuss the parameter estimation. So just keep that in mind. So that's why I was actually going to point it out as well. As I said, it's not n, it's n minus 1. And we'll come back to that later, maybe day after tomorrow. Okay. Or tomorrow itself. Let's see. Okay. And here, as similarly, you know the mode of a PDF. Mode is the value where the function is maximum. So that's basically maximum of f of x at x equal to x hat, or you can say x hat equal to argmax of f of x. Okay, and so if f of x is the PDF of a variable x, then you can also get its cumulative distribution. So cumulative distribution is defined as the integration of minus infinity up to x over f of x dx. Okay, so that's called CDF, or PDF can be written as del f of CDF by del x. Okay, and so suppose this is you can see in this picture, as by definition f of x will go only between 0 to 1 maximum, because the whole integration of the f of x dx is 1. So if you see that, if you have say uh, a PDF like this, which a Gaussian PDF here in this case, and the CDF will be like goes like this distribution. So you can see that, suppose I take what is the value of the CDF at x equal to 4. So that basically means that you integrate from minus infinity up to 4 of this PDF, and that gives you the value of the CDF at 4. Okay. Okay. And the relative quantity corresponding to the CDF is also called the quantile, or order of alpha or alpha point. So that means x alpha is basically inverse of the CDF at alpha. So you can see from here that the median, which is the middle point, okay, is basically when alpha is half or 0.5. So if you take alpha to be 0. When yeah, the value of x where f of x it's basically 50% here. Okay. Okay. And now the another thing that Shilpi wanted to discuss. So this is the characteristic function. So the characteristic function of a random variable with say PDF x, PDF f of x, and CDF f of x, it's a simply defined as the expectation value of uh, exponential of I dx. So phi of t is basically exponential expectation value of exponential of I dx, or you can write this in terms of here, and that basically nothing but a Fourier transform of the PDF with sign in reversal, right? So from this equation you can see that if we know either f of x or capital F, which is CDF or phi t, one of these quantities, the other two can be derived. So one of these will completely provide all the details. Okay. So here in this plot you can see a characteristic function of a uniform distribution which is from -1 to 1. So in this case it is basically nothing but you can see that this is not but sine t over t. Okay, so you can recalculate from this definition and you will find that for within this range it will come out with sine t over t, and that has a distribution like this. But in all cases we cannot actually find easily the distribution because the function can be complex.
There is a question again.
Cumulative distribution. Yeah, cumulative distribution, as I said, the three informations, the PDF, CDF, and the characteristic function are complementary to each other. Okay, so if you know one of them, you will get the other. But cumulative distribution is also used for other quantity to calculate other quantities. For example, here, as I said, that you can find what is the quantile of any, say, any point. Say for example, if you want to find what is the point alpha where the probability is only 5%, so you can find from here, okay, easily using the by using the inverse of the cumulative distribution. Okay,
I have a
like
small example as well, Arun. I can show them like when
yeah,
it
yeah,
can be
okay, that
useful to
will be
compare two distributions, how
yeah,
similar
that
they
will be
are.
useful also. And also another important use is that when you do a variable transformation from one variable to other variable, say if y is a f of x, okay, some function of x, and I want to find what is the PDF of y, then I can use this cumulative distribution to go from one variable to other variable. So that's also helps in doing variable transformation for random variables. Okay. Okay, and there are many properties of this characteristic function. I just listed two, which I think is going to be used in your exercise. So one is that if you have cumulative characteristic function, then this can be used to find moments. Of course, there is also moment generating function as well, but moment generating function may not be also available for all the PDFs. But if moments doesn't exist, but the characteristic function will should exist for all the PDFs. So suppose you want to find the moments for some random variable, that is for say for kth moment, you can write the kth moment here. It's simply I to the power minus k and derivative of kth derivative of this characteristic function at t equal to 0. That's basically this one. So if you take an example, say for example for Gaussian case, the characteristic function is given as exponential of I mu t. Mu is the mean of the PDF minus half of sigma square t square. So sigma is the standard deviation. Then if you take say if you want to find the mean, then you can take the mean, which is the first derivative, and then you can show that you do this calculation, then it comes out to be
I
mu.
think there are two questions now. What
Yeah. Okay.
information characteristic function gives, for example, in case of uniform distribution?
So one information that I am just discussing now is that you can find the say moments, okay, different moments easier in this case by doing this kind of derivatives, okay, nth derivative. Another one is that uh, if you have if you want to make a linear combinations, okay, that is my second point here, that if we have say a random variables x1 to xn, and we want to have a linear combination of these variables. Say if I write some y, which is yh, which are basically linear weighted linear combination of xi with weights wi, okay, then you can write from here you can write the characteristic function of that variable, okay, y can be written like this. So this you can see that if y is sum over wi xi, then the characteristic function of that one is simply the product of the characteristic function of individual xi's. Say if you have just simply sum of the two variables, you have this the product of this two x1 and x2, and from here you can get back the, I think, the PDF easily, if I understood correctly.
Ye- Yeah, we have an exercise on this, so exactly that will demonstrate why it is better to use characteristic functions when we are adding two or any n random variables. It's easier to know their PDF, as you're saying, Arun.
Yeah.
Then the next question is, what do moments tell us? What's the use of calculating them?
Okay. So moments basically gives you the, say if you take the second moment for example, which is a standard deviation. Okay. So the standard deviations, which is a central moment. I'm not talking about the moments itself. From the moments you can calculate the central moments. Okay. The central moments are, okay. Okay. So here in this case, this one gives you the moments, and the whole thing gives you the central moment. Okay. Get central moment. uh, Say for example, if I take the first moment, it is the mean. Okay. And the second moment is the standard deviation. Second central moment is the standard deviation, and standard deviation tells you how much the function deviates, okay, within that, say that whole sample space. Okay, the deviation of the function itself in that sample space. So that's the standard deviation. And I do not remember how exactly it is called, the third and fourth kurtosis.
Third is like how asymmetric the
Yeah,
distributions are, and then kurtosis tells how peak or how flat the distributions are.
yeah, exactly.
So sometimes it is very useful sometimes to see.
Actually, these
I
are
can
very much used in heavy ion collisions.
and
Yeah,
yeah,
we do not use
I
that
have.
much, but heavy ion people use, calculate the
Yeah,
kurtosis and so
one
on.
example coming to my mind, like if there is a jet, just jet from simple a quark jet or a gluon jet,
Yeah.
that will be very symmetrical. However, if it's a jet from, let's say, a boosted Z to BB
Mm,
bar,
yeah.
that will not be symmetrical. So you can form its third moment to see how asymmetrical the jet is. If it's asymmetrical, which means it's not a quark or gluon jet, it's a jet from some boosted particles. So that's what I can
Yeah.
say. I do
Yeah.
not
Yeah.
know if
That's
you have
that's
other
actually a good example as well.
examples.
Yes. Yes. Yeah. Okay. But I think, if I remember correctly, in heavy ion physics they calculate all this to
Yes,
see how
yes.
asymmetric their distributions,
Yeah,
the
yeah,
particle
yeah, indeed.
distribution in the heavy ion collisions and so on.
Yeah, indeed, in heavy ion collisions, it is used more.
Okay. Okay, so I guess, okay, so you can, I guess this when you do the exercises, you will get to know more about this. Okay, and the use of these characteristic functions. Now let me go to some probability distribution functions. So these are some of these discrete probability distribution functions, which are usually called also the mass function, probability mass function. Sorry, 1 minute. Okay, sorry. So let me go to individual ones. So first, let's discuss Bernoulli distribution. So the Bernoulli distribution is basically a very simple thing. So suppose you have a bag of balls, say two types of balls, two different colors, blue and red. Okay, in this case, and every time you pick one of the ball, so you say you get either a red ball or a blue ball, right? So assuming that you have R number of red balls and B number of blue balls, then a random pick will in a random pick, the probability to get a red ball is basically r over sum of r plus p, isn't it? So that's the probability for picking each ball. Now suppose I define a variable x, where which basically defines the outcomes of a trial. So in this case, the trial is picking one of the ball from the bag. So this is called the Bernoulli variable, and the outcome, the value that x can take is either 0 or 1. That means if I pick a red ball, that's my success 1. If I pick a blue ball, that's my failure is 0. Okay, and so you can then you get the probability of x in this case is simply probability of getting 1 is p, okay, to pick the red ball, and probability of getting 0 is 1 minus p. So that's the Bernoulli distribution, okay, which takes the variable in this case only two values, 1 and 0, with these probabilities. Now from this distribution we can calculate also what is the average in this case of the Bernoulli variable. So in this case the average will be, if you calculate this, it will be 0 times p of 0 plus 1 times p of 1. That's basically p of 1, that's p. And similarly the variance will also be p times 1 minus p, okay. And so ratio of uh, mean ratio of p by 1 minus p is usually called the odds. Now from Bernoulli distribution we can go to the binomial distribution. Now consider similar trial but n such independent trials or observations with each having two possible outcomes, success or failure. That means suppose we are picking up many balls, and after say n trials, how many of them are red ball, what is the probability of getting n red balls, okay. So the total probability to have say n success in n trials, you can write say for each trial you have the probability of getting say p or 1 minus p, okay. So if you have say uh, n trials, out of n, if you have say n success, so the probability here will be p to the power n, and then there are another n minus 1 times where you had failures. So we have product of p to the power n times 1 minus p to the n minus n. But then you have the number of ways you can arrange this n out of n trials. Say how many ways you can arrange this n uh, success peaks out of say total n trials. So that will give us as the um, binomial coefficient, which is n factorial over uh, n small n factorial times this n minus n factorial. Okay, so that's like ncn, the number of combinations, right? And so this gives you the binomial distribution. So that tells the probability to have n success out of total n trials, given the probability of success is p, okay. And from here you can actually I give you some exercise here that from this distribution calculate that the mean of n should be n times p, and the variance should be n times p minus p. Now you can see this simple, that earlier case we got the mean to be p and variance p times 1 minus p. Now in this case it is simply a product of n with that, okay. You can see the distributions itself for different values of p and n, okay. So this one the left topmost is for total number of trials 5, and uh, probability of getting success is 0.5. So in this case this gives you, these bars give you what is the probability of getting 0, what is the probability of getting 1, what is the probability of getting 2 success, what is the probability of getting 3 success, and what is the probability of getting 4 success, okay. So the probability of getting 5 success is almost is 0 in this case. And in the left two plots give you for the same probability of success, that is 0.5. If you change the number of trials how the probability changes. So in this case, n is 5, and in this case, n is 10. And the right two plots give, if you have same number of trials, and but the probability of success changes, like the top one is probability 0.3, while the bottom is 0.6, then you can see that how the probability of number of success changes. Okay. Okay. Now, from the binomial distribution, if the n is very large, that means the number of trial is very large, and the probability of success is very small, such that the nu, which is a product of the number of trials times the probability, that means the rate parameter, rate of event, is still finite. Okay, then this you can show that the binomial distribution becomes a Poisson distribution, which you can show here. So let's start from the binomial distribution. In this case, so we replace p to the power n and 1 minus p to the power n minus 1 by nu in terms of nu. So we'll write p as nu by n. Okay, and then from here you can see you can keep this factor. So then we can rewrite this way. So I'll keep this nu to the power n by n factorial here, and then rewrite. So we have this n minus n factorial here. So if you take out this factor from here, then the remaining factor in the numerator will be n times n minus 1 up to n minus n plus 1 by all this n in the denominator here, here, that will come as n to the power n, and then the remaining term here is 1 minus nu by n to the power n. These two terms, I am separating these two terms here from here. Okay, so that's the term here, and then we can take limit n tends to infinity. In the n tends to infinity limit, you can see that this coefficient term, that will become 1, because you have same number of terms in the numerator and denominator, n number of terms, and when n tends to infinity, they will tend to be 1, because okay, and so that will give you 1. And then the second term, sorry, this one we keep it as it is, and this one, so this one, in the n tends to infinity limit, you can rewrite this in terms of exponential of n log this, and then expand the log term here. And since nu by n is very small, that is p is very small, you can neglect the higher terms, okay, in the series, and then you can see that it will come out to be e to the minus nu. Okay, and the third term here, so since this term is very small and n, capital N, this small n is not that large, so this will become uh, 0, so that will make it 1. So then you can rewrite this distribution as f of n given nu. Now we have one parameter, not two. That's instead of n and p, we have simply nu, and that is nu to the power n by n factorial times e to the minus nu. Okay. Now you can see that, say, if we have some observed events somewhere in some experiment, okay, and these observed events, these events are are from some rare process, okay, or which have very small probability to be produced, and then when we get these numbers, they will fluctuate, and those fluctuations can be modeled using a Poisson distribution. And you can show in this case that the mean or expectation value of n would be nu, and also the variance will be nu. Okay, so here this shows some of these distributions. So with the different values of the nu. Okay. Sorry, I think I already took 1 hour. So can I take some more time? I think I have probably 4 or 5 more slides.
Yes, I think it's okay.
Okay.
You can.
Okay, so okay, now I'll go through some of the continuous distributions. So here these are listed many of the important ones which we use. Okay, so let's first come to the uniform distribution. Suppose the variable is distributed between a and b. Okay, then with uniform distribution, then you can write the PDF as p of x is 1 over b minus a if x lies between a and b, and 0 otherwise. Okay, so then you can see the distributions here. So for say if you take a equal to 1, b equal to 4, so you have uniform distribution between 1 and 4. Say if you change the a and b, so you can see the probability decreases, but they are uniform over this range. Now you can calculate the mean again in this case, and the mean will be a plus b by 2, and the variance would be 1 by 2, 1 by 12 times b minus a square. Okay. Uh, Now the next one, which is exponential distribution. Exponential distributions are very important in particle physics, because the unstable particles decay, and their decay rate or decay time distributions are modeled as exponential, right? So the PDF for exponential distribution is given as 1 over tau times eta minus x over tau, where tau is it's a mean lifetime parameter, and you can see the distribution of distribution of x for different values of tau. So as you can see, as tau is larger, the the maximum value is decreasing, but the tail increases. Okay, so in this case you can show that the mean would be equal to the tau, and the variance will be equal to the tau square. Okay, next, the Gaussian distribution, or we also call it the normal distribution. So the normal distribution, which I already gave one example when I talked about characteristic function. So the PDF is written as 1 over square root of 2 pi sigma square exponential of x minus mu square by 2 sigma square, where the mu and sigma are the parameters, and mu is called the mean, and sigma is the standard deviation. So you can calculate from this is that you can calculate from here also that the mean will be mu and the variance will be sigma square, and the distribution as you have seen already. So that's here. In this case, the mu is 5 and the sigma is around 1. You can transform this distribution by doing a say transformation of x, making x to be 0, making mu to be 0, by say if x has mu and sigma, you can make say z, which is x minus mu by sigma, so that will make mean of z to be at 0. So in that case, this is called standard Gaussian, which is you know like 1 over square root of 2 pi eta minus z square by 2. And the cumulative distribution, which I already showed before, is basically you can integrate from minus infinity to z, so that gives you half of error function of z by 2, z by square root of 2. Okay, so this is actually is used the Gaussian distribution uh, is used to calculate say symmetric interval around mu. Okay, so in this case, say if we have so if you take say 1 sigma interval from mu, so that gives you, in this case it's say 68.3% area under this curve. If you take 2 sigma interval, which is this one, this gives you say 95.5% area under the curve, and then 3 sigma interval is 99.7% here. Okay, so that is usually calculated. So if you want to calculate P of probability of having z times sigma, 1 sigma, 2 sigma, 3 sigma, and so on, so that you can simply calculate from the cumulative distribution. Okay, that I was telling earlier, that if you want to calculate the probability of some area under this curve, so you can use the cumulative distribution. So here this in this case you can calculate it from the error function. So this error function of z over square root of 2. So that will give you, so if you use this, that you will get what is the area, 1 sigma area, 2 sigma area, and 3 sigma area. Okay. Now there is a relation between Poisson and Gaussian distribution. So if you have very large nu, the Poisson distribution can be approximated with a Gaussian distribution having mean mu equal to nu and standard deviation, which is sigma, that is equal to square root of nu. Okay. So now you can see this in this plot. So if I take say nu equal to 2, so the lines give the Poisson distribution. Okay, and the dotted lines are the Gaussian distribution. So when nu equal to 2, they are not matching well. As you increase the nu values, the two distributions tends to match better. Okay. Okay. uh, so Gaussian distribution has a relation with the central limit theorem. So the central limit theorem is a theorem which states that if you have n independent random variables xi's, which say their variances sigma I square, then in the limit n tends to infinity, you can have this sum y, which is sum of xi's. They tend to become a Gaussian random variable. Okay, irrespective of the distribution of the xi's, irrespective of the PDF of the xi's, so they will become Gaussian. So with its mean, which is a uh, sum of the means of the independent xi's, and the variance, which is sum of the variances of the independent xi's. Instead of the sum, if you take an average, then you can show that uh, the mean will be the average of mu i's, and the variance will be sigma 1 over square root of n times sum of the sigma I square. Sorry, 1 over n times the sum of the sigma I square. Yes. So uh, where do we use it? Because we tend to uh, model our errors or uncertainties using Gaussian distributions. If we have some uncertainties in a particularly the random sources of uncertainties, we use it Gaussian errors because uh, they are a result of sum of different sources of uncertainties. Okay, which since they are different sources of uncertainties, even if each of these sources have different distributions, since they are combination of many sources, the overall uncertainty tends to be Gaussian. So that's why we often use the measurement errors as Gaussian random variables. So I think I
There's a
will stop here.
question.
Yeah. Or so this is this like factorial moment. Sorry, there are many questions I see now.
No, no, it's the last one, I think. Shouldn't the variance of y contain a 1 by n term as well?
Y contain
Oh,
1
sorry.
by n. Yeah, so this is not average. So when you take average, then it will become 1 by n. So this is sum.
Yeah, we did miss the previous question as well, I realize.
So when you take average, it will be 1 by n. Otherwise, it is there is no. Okay. So there is are moments of probability density functions similar to correlation functions in quantum field theory. This I am not sure. Maybe Partha can comment here if he knows. Do you know Shilpi?
Yeah, I think so, but I mean, isn't it the I think it's slightly different. Maybe Sir can comment as well if he can, because that's more related to the correlation coefficient or correlations that you will discuss tomorrow.
Yeah.
Moments are slightly different because correlation can be between correlation function in QFT is more like between two different wave functions, I think, or I do not know if Sir can comment. If he's there, I think he's connected.
Uh, yes, can you hear me?
Yeah, we can hear you.
Yes. So, um, well, I don't know if Partha wants to comment, but even before going to quantum field theory, um, uh, let's take the simplest quantum mechanics example. When you when you calculate the delta x and delta p, uh,
We lost you. We cannot hear you anymore. Or is it a problem from my end?
No, I cannot hear him as well.
Okay.
No, cannot hear Shatoki, sir.
Okay, let me call him and tell. I'm unable to reach him. I think when he connects back, we can take this question. But to me, it seems like eh, moments are more like within a same distribution. What are
Yeah,
the characteristics of the distribution? So,
Hello.
yeah, Partha, we can hear you.
Is there anything? What is going on? Sorry.
No, so no, there is a question which we are not sure. Satyaki
Oh,
was
okay. Okay.
answering that.
Sataki is also there. Okay. 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 So, what is the question?
So there is this question that are the moments of probability density function similar to correlation function in quantum field theory? Maybe
Oh,
you know.
this moments of probability you are discussing, no? That
Yeah.
is
So is this similar to the you mean this is relation to the correlation
conceptually very similar, but
Okay.
they are very different object
Yeah,
altogether.
that's what I was thinking. I
Yeah.
mean,
So
yes, not
means
exact.
otherwise
Yeah. Okay.
conceptually they are similar. Means you can say that there is a correlation function in a probability system, but those are the space-time points in quantum field theory. So you are associating those with this two space-time point in a n-body function, means n-point function.
Okay, okay. So when we come back to the covariance matrix, you would probably say similar. For the moment, these are within the same distributions. They are
Yeah,
not too different. So maybe when we have the off diagonal elements of the covariant matrix, so we'll discuss that.
yeah,
So
yeah.
where there we will have the correlation, and then probably it will be very much similar.
Right, right. Yeah.
Mhm.
So
um,
you have finished already, no?
My part I completed, so I'll go the rest of the things later. So I can probably
Satyaki was telling something probably.
yeah.
yeah, sorry, I don't know, my system rebooted. So yes, I was telling that even in quantum mechanics, in the very first proof of uncertainty principle that you do, delta x, delta p, they are just the standard deviations or square root of variances of x and p, um, uh, taken over a Gaussian distribution.
Yeah,
Correlation, yeah. So
yeah. So the delta
and
x and
then
delta p itself are similar to the central moments. I mean, the deviation, standard
yeah,
deviation.
so
Yes,
it's they're the second central moments of the measurements of x and
yes, yes,
p.
yes.
Those outcomes are random variables, the measurements of x and p. So and as Partha said that the correlation, let's say the 2 point correlation in field theory, they're related concepts, but it's you do not calculate these quantities over a PDF. Um, like like the classical PDFs that we have. we are talking about here.
Hello. I think this is the all the same. In quantum field theory, we use usually functional variables.
Yeah,
Otherwise,
functional
all are
variable.
same.
But they are two space-time, defined space-time point.
Yeah, that's why it is functional variable.
Yeah, yeah,
But
you can say that way.
we all are differentiate the say minus infinity to plus infinity, right? When you take the correlation function, we usually in the time space, we
Yeah,
usually integrate minus infinity to plus infinity.
yeah,
That's all.
yeah, yeah,
Here
yeah.
also same.
Yeah, yeah. Conceptually, they are same. Exactly.
Yes.
So we'll go for the quiz now.
Yeah, I let me stop.
I think Amir, are we ready? He's there.
I think he made some comment 15 minutes before.
Oh, where is he? Amir, I don't see his comment. Arre, I cannot do that. Only Amir can do that. Otherwise, we have to continue with this next part.
If you want, I can. I think I also have the rights to conduct the quiz.
Yeah, I
It's
think.
about closing, and because it's better
Sorry,
if we
I'm
have the
back.
quiz
Yeah,
now.
Yeah,
I'm back.
I think let Shilpi start, and after finishing, we'll go for this quiz part.
If
Okay, yeah.
Amir is there, it's better that the quiz
No,
happens.
I think he's now back.
Yeah, I'm back.
Yeah.
Yeah, I
Oh, okay,
think I
okay.
Okay.
lost the connection.
So
So,
tell
okay,
us
so
what
should we
you
conduct the quiz or should we wait
Yes, yes.
after?
No, no. Please go ahead with the quiz.
Okay,
It's fine.
okay. I'm sharing the link in the chat.
I
yeah.
think we can have maybe half an hour
Uh,
tutorial today, and you can
It
move
is
to
only
next.
5 minutes probably.
so yeah, the quiz is for 5 minutes.
It's just five. It should take just 5 minutes,
Yeah, should
not
yeah, it
more
should
than
take
that.
less than
Yeah,
five.
or at
So
max 8 minutes.
yeah,
Okay,
so yeah, I have shared it over the chat. So
okay,
please,
good.
yeah.
Yeah, and you count down and you.
So yeah, we'll stop like accepting the responses exactly on 3:56. So please,
Okay, okay. 1 minute 30 seconds before.
yeah, sure, sure. Yeah.
Huh? Yes,
Yes,
Pooja.
yeah. Oh wait, it's rewind. Yeah, Pooja, you can ask a question.
Shilpi, is there slide for you, or you will do it?
No, no. I have a Google Doc I can share with them with questions, and then I have some half written codes for them, so I can share both the links.
Oh, okay.
So there is a question by Pooja. I lost my connection for a bit. Has the link been sent? Yes. So we are. I'm resending the link.
Pasted, yeah.
Oh,
Okay,
okay.
the link has been pasted. Yeah. Okay, you have 1 minute left for the quiz. Can we leave?
No, you
Yeah,
cannot leave. I think we have tutorial.
yeah, there's a tutorial. So no break.
We can have 5 minutes break. It's fine.
You want to give 5 minutes break?
I mean, if people want, it's fine. I can continue tomorrow also. Yeah, yeah. I
Arthur,
mean,
what do
today.
you suggest?
Uh, is it too heavy for the students? I think, yeah, means part of the first part of the lecture was not too heavy, but I don't know. Means for PhD students, they have some exposure. No?
So yeah,
Okay,
they are asking for 5 minutes.
some of them are asking for 5 minute break. Probably that is okay. Then we can come back.
Okay. So will there be another quiz today? I don't think so. Yeah, there won't be another quiz. This was the only. Do we need laptop for the tutorial?
Yes, of course you will need.
But there was tutorial in Python, no, earlier. Students should have
I have a power cut at my home, but I think the docs would be shared, so you can try later on
yeah,
if
okay.
you have some power issue.
There are some things that you can solve on pen and paper, but there are some exercises that will need your laptop.
Okay, so we'll meet at what 4? What's the 4:05?
Yeah, maybe that is okay. And yeah, you closed that quiz already, no?
Yeah, yeah. Let me close. Yeah. So okay, we'll meet at 4:05 if that's what.
Hadron-hadron collision data. So what happens in hadron-hadron collision? There are many jets everywhere, and these jets are essentially spray of particles. They contain a lot of pions, they contain neutrons, protons, mostly pions, pi plus, pi zero, and pi minuses. And pi zero, 99.99% of the times that decays to two photons, and hence it can give you like an electromagnetic signature in the electromagnetic calorimeter. And because there are several tracks in the jet, so that um, that cluster of energy in the electromagnetic calorimeter can match with a track also. So essentially these jets can look like electrons in your calorimeter. So the question is, so you essentially apply some identification criteria to separate out true electrons from these fake jets. So suppose our identification criteria using the shower shape and tracking variables, suppose that gives you an efficiency of 90% for true electrons, meaning if you have a collection of true electrons out of 100, those criteria lets only 90%, 90 electrons pass. At the same time, using our selection criteria, 1% of the jets are also misidentified as electrons. This is what I was just telling you, that jets can fake as electrons. And suppose our event sample contains 8% of the real electrons and 92% jets, what is the probability of a candidate to be an electron if it passes our identification criteria? So this is, I think, okay. So, how would you estimate that? Can someone tell me? I think it's like uh, this might be straight exercise for most of you.
Through base theorem, we can approach this. Like we already know that uh, the
Uh-huh,
electron identification criteria has been passed.
uh-huh,
So we
uh-huh,
have to find the event like probability for the that particle to
mhm.
be electron given the criteria is passed, and we
Yeah,
already know that what are the other things. This is similar to the
yeah,
question that we practiced earlier in the tutorial in the
yeah, yeah,
class itself.
yeah. That's good. So maybe then you can take like 5 minutes and tell me the answer, or less than
Sure.
5 minutes. But if something is not clear to someone, please don't hesitate to ask. Is the question clear to everyone?
Yes. Go ahead.
Okay. Okay. Can someone tell me the answer?
88.6%.
Yeah, perfect. I assume everyone has done this, so I'll move to the, yeah, I mean, you're giving me an approximate answer. It's actually 88.6%. So Prajita, can can you tell how you did? Are you getting 87? Okay, you can check again later, but I'll post the solution. Yeah, I'll post the solution later to this question. Um, we can move to the next exercise, and that is related to the quiz as well. So this will help you familiarize with the probability distributions and when to use what kind of distribution. So there was a question that if a detector has limited efficiency for detecting a particle, then how would you simulate the number of muons detected? So essentially, the question is, if there are 100, if there are 100 muons coming one after the other hitting your detector, so what kind of distribution would the number of muons which are detected will follow? So let's say I did an experiment in which I shot first 100 muons to the on the detector. the efficiency is 70%. You might think, okay, you will get 70% of the muons. But then I do another experiment with 100 muons and then again shoot on the detector. Will you get 70, or what kind of number will you get? So this is related to whether, so the outcomes are two. The detector can either detect it or not detect it. So which means if the outcomes are two, so it should follow which distribution? Can someone tell me? Binomial. Okay. So so can you do an exercise in which you conduct such 10,000 experiments, and in each experiment you shoot 100 muons with an efficiency of 70% and see how it is distributed. I'll just share a notebook with you, link to the notebook. Is the question clear to everyone? Okay. So I have shared the Cernbox link with you. You can click on various distributions, various underscore distributions underscore exercises. So then you can see if you increase these number of muons hitting your detector from 100 to, let's say, 1000, uh, can you tell me what kind of distribution it starts assuming? You can speak up because I'm not always sorry, what do I repeat? Can you please interrupt me because I'm not always looking at the chat window. So what is being discussed? We are on this first exercise where there are 100 muons. Let's say they are hitting your detector and your detector has a detection efficiency of 70%. So the question is, what kind of distribution will the number of muons detected follow? So let's say you did your one experiment is shooting 100 muons on the detector. Let's say it has a 70% efficiency. So sometimes you will detect 68, you sometimes will detect 71, sometimes 70. So what kind of distributions will that follow? So essentially you should check this. So let's say instead of 100, I am so people are answering Gaussian. So let's say instead of 100, let's say we have 10. Will it still follow Gaussian? So this is so the detector, it has two outcomes. Either it will detect or it will not detect. So which means it is a
It's a
binomial
Bernoulli
distribution, right? It is a
Bernoulli process.
yeah, exactly. It's a binomial distribution then. It's a you meant binomial distribution, so it will follow binomial distribution. But as you keep on increasing this n to, let's say, 200, 500 or 1000, you will see that it will approach Gaussian. Okay. So I guess I will not wait for this one you to complete. I think you can do this exercise, but I'll send the solutions as well later on. I hope this question is clear to everyone. Okay, fine.
Yes.
Okay, good. So now let's move to the next exercise quickly. Sorry. Okay. So then In a fixed time interval, the expected number of cosmic ray hits on a detector is lambda equal to 3. So if you have 10,000 such intervals, and then you look at the distribution of these cosmic ray muons hitting your detector, what kind of distribution will it follow? This was a question in your quiz as well. So because this is
Also,
about number, yeah, this is about number of, exactly, this is about the number of events or number of cosmic ray hitting. So this always follow Poisson. But then you will see, as you increase your lambda to, let's say, 10, 11, or 12, it approaches Gaussian. So you can do this exercise again. Now, this exercise is very important. You do any analysis. So this is about when you suppose you have a detector, and if you shoot, let's say, 100 GeV photons on it, and would you always see 100 GeV energy as the output? You will not. It will not peak at 100 GeV. Why? Because detector has a finite resolution coming from its inherent noise, maybe limited number of photostatistics if it generates scintillation photons, or there can be multiple other reasons. So it has a finite resolution, which means if you shoot 100 GeV photons on a detector, it will sometimes be detected with an energy of, let's say, uh, 95 GeV, sometimes 105 GeV, or 101 GeV. So it will have a distribution, and let's say the spread of the distribution is 2%, meaning 100 GeV with a 2 GeV of spread. So what kind of distribution will it follow? Because it has equal probability of giving both sides of 100 GeV. So it's a symmetric distribution.
Probability Gaussian.
Yeah, exactly. It's Gaussian, and it comes very handy when you do your analysis and try to um, smear energy. You will require this. So I think you can do the exercise, this one as well. Now, okay. So the last exercise in this question is generate toy Monte Carlo for isotropic decay of a scalar particle in its rest frame. So, can someone tell me, if uh, there is a scalar particle sitting, and if it decays, what kind of angular distribution will its daughter particle take? Will it be symmetric? Will it be uniform in theta, or will it be uniform in cos theta? Yeah, that is the question. I think I have already written by mistake. Okay. So maybe I can ask, why will it be uniform in cos theta but not in theta? Can someone answer me? Anyone?
Ma'am, probably because uh, in an isotropic decay, particle decays almost equally in all directions. So maybe
Yeah. So you could think that theta should be then uniform. Why is it not uniform in theta? Why is it uniform in cos theta?
the solid angle is given by sin theta d theta.
Exactly.
because
Exactly. Yeah. Yeah.
the shape of the
Absolutely
cos
right.
curve is
Yeah.
uniform.
So someone said about solid angle, and that's absolutely right. So essentially, you can imagine the scalar particle sitting at the center of the shell, and when it decays, when we say that because it's scalar particle, so it has no preference about the decayed particles, no, nothing to conserve in no preference about the spin. So when it decays, it if you take a small element in a shell, um, you will find it uniformly distributed in the other directions also. So small element is let me actually write. I'll just stop sharing from here. Stop sharing. So what I was just saying is that if there is scalar particle sitting in a shell, then if you take a small solid angle here, then in all such solid angles you will find uniform distribution. So that small solid angle is, sine theta, d theta, d phi. And then what we are saying is dn by d omega is constant, which means dn by sine theta d theta can be written as d cos theta, which means it's in cos theta that is constant, you see. So it's constant in cos theta. Um, so so um, so then you can now generate, if you want to look at the distribution of theta, then you just throw a random number, a uniform random number uh, from -1 to 1, and then do an a cos to get the theta. Is that all right for everyone?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes.
Okay, good. Um,
So this Shilpi, this is for single particle, right? Not for angle between the two particles, right?
yeah, not between the angle. I'm sorry, I just I cannot unshare. Yes, it's not between the angle between two particles. I cannot unshare right now. Sorry. Okay. Okay. So so then now let's go to the third exercise. So here someone had asked how to use, okay, so let me just ask you. So if let's say there are exponentially distributed random variables, n, let's say 2 or 3. Let's start with 2. Okay, and let's say the parameter of the exponential that decay is lambda. If I sum these two variables, how will they be distributed? Let me start with 100 actually. So let's say if I have 100 such exponentially distributed random variables, so how will that be distributed? We learned some theorem today. Anyone? Exactly. It will be Gaussian via central limit theorem. Very good. But when it is 2, then it is not Gaussian, right? Because central limit theorem works only if your n is in the limit of large n. So when it is 2, or when n is small, then how do you get the distribution of sum of two random variables? So can someone guess what, how
Binomial.
can? No, it won't. That you cannot guess like this. It won't be binomial. Why will it be binomial? It doesn't have two outcomes, right? So
Poisson.
okay, why don't you then solve this and check? Uh, how will you approach this problem? So I can give you a hint. Um, so hint is use characteristic functions. Can so I think Arun, have you already shared your slides?
No, I can show
No?
the characteristic function.
If you could please show the characteristic function, then I think this will be a good idea to learn how to use, because someone was asking where and how to use characteristic functions.
Yeah, but for the exponential, I think I do not have in my slide.
Sorry?
Yes, sir.
There's a, sorry, someone has to mute. Sorry, someone has to mute. Questions are not visible.
Amir, you are there?
Yeah, I muted him. Yeah.
You can drop my slide here. I think if that helps. Can it be actually dropped? I don't know. Attachment.
Questions are not visible. No one can see the questions. I shared the link.
The question link was shared.
Let me share it again. Let me share again, and I had pinned it also. Let me just do it again.
You shared earlier.
So I'm on exercise number 3. Can someone try to solve this? Then I can give you a second hint also. So how will we approach this problem? Okay, let me actually just give you all the hints. So what we will do is, I hope you can see my hints now. Right? So essentially, what will you do? You will first use this property of characteristic functions, that sum of the characteristic function of sum of two random variables is just the multiplication of individual characteristic function. That is one property to use. Okay.
Can't see the screen.
Then the second property that you will use is, you will first find out what is the characteristic function corresponding to one exponential. Then for the second exponential, you will just multiply. You will just multiply. Then the second, I can give you a hint that sum of two, let's say, two exponentially distributed random variables, they follow gamma distribution, which I think we did it today. So then you just you know the PDF of the gamma function here. Let me share my screen. Actually, I'm not sharing it. Okay. Then you know the PDF of the gamma function, evaluate its characteristic function, and you will see that the characteristic function of a gamma function is exactly same as the characteristic function of sum of two exponentially distributed random variables. I can repeat again if it's not clear. Shall I? Okay, I'll do it again. So essentially, the idea to you is to use characteristic function to determine what will be the PDF of sum of two exponentially distributed random variables. How will you use it? The first property that you will use is that sum of two independent random variables, their characteristic, the characteristic function of sum of two independent random variables is just equal to multiplication of their individual characteristic function. That is first one. Then you will find out the characteristic function of an exponential distribution. Then you can get the characteristic function of sum of two exponentially distributed random variables. So that you can call as equation 1. Then I'm just giving you a hint that it follows gamma function, that when you sum two exponential distributed random variables, then if you look at their distribution, that follows gamma function. So then what you can do, you can find out the characteristic function of a gamma function. Then you will see that the characteristic function of a gamma function is the same as the characteristic function of sum of two exponentially distributed random variables, which means that sum of two exponentially distributed random variables, that follows gamma function. Are the steps clear? If not, then I can do the exercise. So the idea here was to show that is to say that if you keep on increasing n, you should use this code, which is named. I hope everyone could access the CERN box. You can use this code, sum of NEXP. So the idea here is to see that if you have sum of two exponentially distributed random variables, it's highly asymmetric, you will see, and but that the gamma PDF can describe this distribution very well. And as you keep on increasing this from 2 to 5 to 10 to, let's say, 100, you will see it very nicely approaches Gaussian distribution. Okay, so now um, let me just show you how to approach this.
Are you sharing?
Starting to share.
Okay.
Okay, so I hope the question is clear to everyone. What are we trying to understand? Just how is the sum of two exponentially distributed random variable distributed? So let's say I have two random variables x and y, and I want to see how is this w distributed, right? So first of all, characteristic function of a random variable is is essentially just the expectation value of this itx, which means it's an integral from right. That's how you define expectation values. Now, now today, what you saw in the slides is that the characteristic function, sorry, of sum of two random variables is just the multiplication of, you can see that in the slides how it is, but it's very easy to see. Okay, so this is what we will use. Now let's determine the characteristic function of an exponential function. The reason we are doing this exercise is because sometimes you really do not know. Let's say there are two uniformly distributed random variables, how will their sum be distributed? Or if there are two Gaussian distributed random variables, how their sum is distributed. So you can always, either you can just do you can just do your exercise. You can just write a small code and see how they are distributed. But this is actually a very straight and simple way to see quickly how things are distributed.
Shilpi, what is W in your notation?
Oh, sorry, W is this. I already wrote
Oh, okay. Yes.
sum of two random variables. Okay. Okay. So then, imagining that we are looking at the time. So for an exponentially distributed random variables characterized by lambda uh, uh, minus lambda x dx. So that's the exponential distribution, right? So if you integrate between the limits 0 to infinity, you will get for two random variables. Okay, so this will be lambda over lambda minus it. Okay. So for uh, two random variables coming from characterized by the same lambda. So again, writing w is equal to x plus y, characteristic function of such a variable would be just using this property what I wrote, lambda square by lambda minus it square. And if these are n variables, meaning x plus y plus z plus t till n, then for n it will become okay. So this is the characteristic function of sum of n exponentially distributed random variables. Okay. Now, if we can show that for a gamma distribution, if the characteristic function looks like this, then that means that sum follows gamma distribution. So now I already wrote that a gamma function, it's a two parameter function. And in the Google Doc, I have written how it, what kind of distribution, how it looks like. Okay, I can take this to be lambda, the same parameter. Okay, then its characteristic function will become of this gamma function. Sorry, uh, will be, I should write it x here. And then this whole function comes here. Okay, and now you can use this property. I hope everyone can see the Google Doc. You can use that property from the Google Doc, that gamma of E by BA. I'll write down. We are just making use of properties. So you can see your A is n and your B will become lambda minus IT. So then the characteristic function of a gamma function just becomes lambda to the power n by lambda minus IT to the power n. So you can see this expression and this expression, these are the same. So what I will give you as an exercise, if you can do at home, just you can use the notebook that I shared with you. Just throw two exponentially distributed random variables, take their sum, do such, put that in a histogram, and then do this, let's say 1,000 times or maybe 10,000 times. You will see it's a very nice, it will, and then fit with a gamma function. You can find the libraries yeah, in SciPy to do the fits. So you will see that it very nicely follows a gamma distribution. And it will be asymmetric, but as you increase n equals to 2 to 100, let's say, you will see the shift, that they shift to Gaussian. So I hope this exercise is clear to everyone. Is it? Okay. Okay, very good. Then let me go to the last exercise. So here it will take some time, but this essentially tells you, someone had asked, how can we use the knowledge of our previous experiment and uh, and put that as in a prior and base theorem. So essentially the question is, let's say you have a coin and you toss it 100 times and the number of heads is 70. You say that it's an unbiased coin, right? But how will you use Bayes theorem? So let's say, uh, so out of 100 tosses, your number of heads is 70. So I might think it's a biased coin. So the
Sorry,
sorry.
someone is requesting to share the notebook again. There's some message.
Okay. Yes, I was not looking at the messages. Okay. I'll just share the notebooks. Can you see this now? Okay. Um, okay. So essentially, now the question is, how will you use Bayes theorem to arrive at the conclusion that the coin is biased or not? So essentially this question falls very well when we come to hypothesis testing, but I thought that this might be a good idea to show how to use Bayes theorem. So has everyone got the idea of the question? I think some of you have done this exercise, but most of you probably haven't done this. So has everyone got the idea of the exercise? Okay. So since no one is answering, I'll just move ahead. So essentially, the way we will approach this problem is the following. I'll again share the screen. So let's say when out of 100 times I obtain 70 heads. So let's say my belief is that the coin is biased, and that uh, it's speaking. I have a firm belief. I have a very high belief that the probability that the p of that the probability of obtaining heads is 0.7. Okay, it's not a nice Gaussian. I was trying to draw Gaussian. Okay, and then it starts dying down. So on the x-axis, what you see is the probability of obtaining heads. This is my belief. I call this is my prior. Okay, sorry about this drawing. It has to be a Gaussian. And a y-axis essentially tells the height, essentially tells how good is my belief in that probability. So because I did the experiment just one time, I say that the probability of obtaining heads, I have highest belief in obtaining the number of the probability of obtaining heads is zero 0.7, and then it starts dying down, meaning if I go, let's say, 1 sigma away from here, then my probability is reduced to 60% of 60% of what it was here. Okay, so then what you will do is you will conduct, let's say, 1,000 experiments. In each experiment you will throw the coin 100 times. Then you will look at the number of heads, and then you will use the Bayes theorem, whether the coin is biased or not, given. So you did, let's say, first experiment. Okay, then I'm sorry, I think online teaching is a bit tough for me.
Yeah, writing here is very difficult unless you have a tablet.
No, I'm using the tablet only.
The tablet, okay, same.
I'm not used to, actually.
Yeah, may I suggest that you use a thinner pen width and maybe
Yes, I had reduced it. Okay.
yeah, choose a different pen, not the
Okay.
one which has its head cut.
Okay, yeah, that's right. Yeah, now it's better. Sorry.
Yellow, the color is fine.
Okay. Okay. So essentially what you will do, you will conduct one experiment. Let's say we conducted one experiment, and we will so we start doing the experiment. We will let's say we obtained um, we obtained, let's say, 50 heads, and then I will just use use the Bayes theorem. um, sum over all such possibilities. Okay, so what I will do is, um, maybe I should go to the code. That is easier for me to show. I'll show the code and then you can write on your own. Okay. So essentially, so first of all, I assume that the probability of success is zero point 0.7, and success is defined by whether I'm getting ahead or not. And then I just form a prior. Uh, so at each, so essentially what this is giving you, at each location of P, probability of getting a success, I'm getting uh, a height, a Gaussian height. So this is what I formed as the prior. This will give you a Gaussian distribution. So at 0.7, you will see that the height is the highest, and then it dies down around zero point 0.7. Then what I will do is I will start doing the experiment. Let's say I did one experiment of 100 coin tosses. Then I feed that my belief in that Bayes equation. This is a coin toss, so the probability of getting in heads follows the binomial distribution. So then what you do is you just get the posterior. I hope you remember. I think Arun, you had introduced the term posterior, right?
Yes.
Okay. So then what you get is you get some information. You apply the binomial probability of getting that many heads in one experiment. Let's say you got 50, and then you apply your prior, whatever your belief was. You get a posterior out of it. Now when you do next experiment, you see there is a loop, right? So when you do the next experiment, that posterior of the previous experiment becomes a prior of the next experiment. And as you keep on going this experiment, keep on going doing this, at the end, if you look at your posterior, you will see that it very nicely approaches uh, zero point 0.5, because I started with an unbiased coin. And although my belief earlier was that it is a biased coin, peaking at zero point 0.7 as the probability of getting a success, you can see that after repeating many such experiments, it very nicely shows that it is an unbiased coin. Is this and one thing you will see that wider is this distribution, lesser is the number of experiments that will take you to reach to this conclusion. If your belief is looser, meaning if you do not have the firm belief, it is much easier to get to the final correct inference. But if you're
When you choose this Gaussian, how do you choose the sigma for that?
that exactly, you can just choose anything. If I choose let's say if I choose a wider sigma, you will see that the number of, just a second. Okay, I'll just run this. You see it's 18. So you can choose any, depends on your belief, no? If you have a very firm belief, So very firm belief will mean, let's say from point 3 to point 1. It takes you, okay, it's taking lesser trials. I do not know why. It should have taken lesser trials. Okay. But sigma is just depending on how firm your belief is on your assumed prior.
So
Is
LOC is 0.7 in your case, right?
sorry?
The starting LOC value here is 0.7.
Exactly, because in the first experiment when I did, that was 70 heads out of 100 coin tosses.
Okay.
Is this clear? At least I have shown you the code. Maybe I can explain you by writing as well. But are there any questions on this part, or you did not understand anything at all? So posterior probability of n minus 1th experiment, yes, will be the prior of the nth experiment. Exactly. You keep on feeding your information from the current experiment to the next experiment. Can people raise their hands if they understood? If they didn't understand, it's fine. Don't raise your hands. I can explain again. Okay, I don't see much hands raised, so maybe I can explain again. Maybe I should explain again.
I see that many people have raised hands.
But the fraction is very small. Not even half.
Yeah, only 16. Yeah, 18 more.
Okay, I can, which means people did not follow much. About the approach. Okay, okay. Okay, right. So I can tell you about the approach. Just a second. So essentially the approach is that, so the question again. So the question is, someone tossed, there was an unbiased coin. Okay, we already knew that that was an unbiased coin. Someone did 100 tosses and you get 70 heads out of it. So your belief might be that it's a biased coin, right? Because you're getting 70 heads. So the question is, how will you use Bayes' theorem to show that it's an unbiased coin? So the question, in order to tackle this question, you have to do many such experiments of coin tosses and many such experiments. So in each, so what you will do in each experiment, you will use Bayes' theorem. You will first start with your belief. So my belief is that the probability of getting heads, the probability of getting heads is 0.7. I'll just start with this belief. And I'm not saying that I completely believe in that. So that's why it's not a sharp spike at 0.7. I say that I have a good belief. So that's why it's Gaussian. It's not a sharp spike, it's a Gaussian. So, so
Hello,
then,
ma'am.
yes, yes.
Sorry to interrupt you, but
Uh-huh.
I have a doubt. When we are saying our belief is like it is a first biased coin and our peak sharp at 0.7, but
Uh-huh.
uh, I'm confused with the prior thing because I can see it's kind of array, and there you have defined it in a random number, and then again for the k in t, there we have a Gaussian curve. So I'm confused
Okay.
with these three things. Like how
Okay.
my
Okay.
belief you are turning it into this kind of thing. Like
Into
either
an
you are
array.
turning an array
Okay.
or
Okay. Okay. Okay.
whether
Okay.
it
Let
is
me.
a okay.
Uh-huh.
Okay.
Okay. Okay. I got your question. Let me actually then go line by line. Just let me go line by line. So this line, what this line is doing, this line is essentially generating. I was saying that do many such experiments of 100 coin tosses, right? So this is just doing 300 such experiment. Um, so okay, I have taken 10 coin tosses. Fine. So what it is doing, it is doing 300 experiments with a coin, which is an unbiased coin because the probability is zero point 0.5. I've started with 0.5, and each experiment it is doing 10 coin tosses. So what random numbers this gives you, it's an array of size 300, and each element is the outcome of that experiment. Okay, this
Got it,
line is
ma'am.
clear. Then
Yes.
what this line is telling, so now this is dividing essentially uh, a line from 0 to 1 in 500 equal parts. Why? Because at each point, so essentially you can assume this as my probability of head. So so this will be, first will be 1 by 500, second will be 2 by 500, right? So at each point it will calculate, it will, it is essentially the height of the Gaussian. So the x-axis sort of represents the probability of getting head, and the height tells the belief that I have in that. So essentially, I'm just generating an array of numbers uh, uh, for each probability value of success. Okay. So I can show you this distribution maybe. So this is going from 0 to 1. So here uh, at 0.7, my belief is the highest, meaning probability of success is highest here. And then it starts dying down, right? So you just need, this is essentially forming the x-axis of this thing, so that you can evaluate the height of the Gaussian at each value of the possible probability value.
Okay, ma'am. Got it. Thank you,
Okay.
ma'am.
Okay. Then what this is doing is, this is just at each p-value, this is just calculating the height of the Gaussian and putting that in the array. That's why it is an array. This is an array so that I can plot it easily like this. Okay.
Okay, ma'am. So with each experiment, we will update like what we are getting as a result, which will be shown in the y-axis. So at
Exactly.
zero point
Exactly.
0.5, we are getting a highest same number of that.
Yeah. In the end, when we did
Mhm.
300 such experiments, we could arrive here. Now, what we were discussing in the end is that larger is my width of the prior, meaning if my belief is not firm, it is quicker to arrive at the uh, actual result. But if my belief is very firm, let's say the width is small, then it takes more number of trials to arrive here. Okay. And essentially, then what this line is doing, so let's say, so for each experiment, what it does is it takes first this probability value, okay, and then it calculates the prior, meaning it calculates this value, the y-axis. Then for the same experiment, it moves to the next probability value, then calculates the prior, meaning the y-axis. And that's how after each experiment, you obtain one such distribution. Once you have obtained one such distribution, we call it posterior. We feed back into the next experiment. You see that prior became my posterior.
Okay. So with each experiment, with each trial, our prior get updated based on the posterior, whatever we are getting
Yes,
as a result.
yes,
Okay.
exactly. So what I will do, I will share this code with you all. You can have a look at it today and then we can discuss tomorrow if there are any confusions.
Okay, ma'am. Thank you, ma'am.
Yeah, no problem. Anyone else has a question? Otherwise, we can take it tomorrow. Okay. I don't see anyone has a question.
Yeah, there is no question on the chat also.
Yeah, I'll share the notebook with you all, and then you can have a look at it how we have done it, and we can discuss this exercise tomorrow. Okay, I think I'm done for today.
Okay,
Thank you, ma'am.
thank
Yeah,
you.
welcome.
Thank you, ma'am.
Uh,
Thank you.
Actually, ma'am, I have a request.
Uh-huh.
Can for the next session, can we also talk about the pseudocode? Because we also want to learn like how to do it and like approach the question on our own, like how to proceed with the code before. Like,
Yeah, right.
are you
Mhm.
getting my point?
Yeah,
Like,
yeah, yeah. You want to do the exercise on your own, right? Okay.
yeah,
Yeah,
with the pseudocode help only, because we
uh-huh,
want to see like whether we are able to do it or not. Because when we are seeing the direct code, it is
uh-huh.
quite clear, we get it easily. But when we
Uh-huh.
have to think our own on our own, so it becomes quite difficult.
Yeah,
So
yeah, yeah.
I
No,
just
no.
want to learn that process as well in this
Sure.
pre-summer school.
Yeah, yeah, sure, sure. I mean, that is what I thought I will do today, but somehow, because we were running out of time, I just did all the exercises with you. But tomorrow we'll certainly approach it that way. But
You
I,
can, in the
you
meantime,
can
try
also
to do it yourself in your.
exactly.
Uh,
You have the Google Doc with you, so don't look at the answers before. You can just approach it now on your own. Even if I have explained you, just try to approach it on
Okay.
your own because for sure it's not 100% understanding. So try it on your own.
Okay. Okay, I'll try that. Thank you for your time. Thank you, sir,
Yeah.
ma'am.
Okay. No problem. Okay. I think that's it for today. I'll share the codes.
Okay, that's all today. So I think switch off this recording and
Yeah.
okay.